Thank you for joining as we talk about managing the IoT. IoT is a overused term, and so we're going to focus here on what IoT means to the service provider community. I'm Ed Shrum. I'm with Cox Communications, and I lead the product development team for our residential and devices and small medium business as well. Today we're going to hear from some of our leaders in our industry to help us understand how do we manage the complexities of IoT, security and privacy aspects of IoT, and then how does that map down into the CPE we put into the home, and how do we understand, how do we manage the various types of technologies associated with IoT and how they map into the gateway platforms. The format today will have three presenters. We'll hold questions until the end, so everybody has a chance to give their presentations, but we'll leave plenty of time at the end for questions. First up, we have Michael Shaw, who is the Chief Executive Officer at Axiros, which is focused on carrier-class enterprise device management for communications and Internet of Things applications. Prior positions, he was the Chief Solutions Officer at Connectivity Selden and the Global Vice President at Cheetah Technologies.
Great. Thank you.
Get you started, Michael?
Certainly.
I think you're off and running. Yep.
All right, good. Should we say seated or stand up? Any preference? Okay. Good. Hello, everybody. You got a mic up there. Oh, awesome. I'll do it from the dais. All right, then. So thank you very much. My name is Michael Shaw, as Ed mentioned. I see some friendly faces. I see some folks that we might have worked with in the past. I'll start by setting the baseline for knowledge for some of the introductory remarks. Is everybody here, or is anybody here familiar with an ACS auto configuration server? Show of hands. Okay, good. TR69? Excellent. All right, good. So one of the things that we're going to get into today is talking about there we go. It's animated. TR69 is a baseline for the conversation about what is now called user service platform. It started out as universal. Somewhere along the line it became user. But user services platform is a good example of a name that describes the function of the technology, and it is an evolution of TR69. So what we're going to be talking about now is how this has become involved since its release late last year in the efforts to try to find standards for embedded technology and server-side applications that make connected devices easier to manage and enable services. So the evolution of TR69, which is widely used around the world for provisioning, is based in part on an ACS or controller that uses a standard communication protocol connected to a data model within a device. The TR69 stack can be implemented fully, well, poorly, but it will depend a lot on what are the aspirations or goals of the company who is manufacturing a device, the one who is implementing the stack, and like every other kind of standard, it can be used universally and for global application, or to do very specific functions for a managed ecosystem. So we're going to talk a little bit about that. The universal design of TR369, which is the technical report name for USP, is important because what it does is it standardizes the technology on both the controller and the agent side. And that becomes particularly important in the Internet of Things, where what you're looking for is you're looking for ways to provide a safe investment environment for advancing technology, but that you're addressing all of the concerns that need to be addressed from a security and from an efficiency point of view. As a lot of us know involved in this industry, it's easy sometimes to get involved with technology debt. The use of a standard like USP seeks to address a lot of the concerns of the modern connected world without establishing a lot of technology debt that needs to be dragged along. So the potential for it has a wide implication in the cable industry. Did I have a question? Okay. Let me say we will have a no. Noise is fine, and so are questions. I'm an economist by training, so if I use any strange analogies, you can interrupt. But if I've been involved in cable long enough to know that dialogue is more interesting sometimes than just presentations. So we'll have some questions and answers, but if you have something that comes up in the meantime, feel free to address it. All right, good. So the Internet of Things and cable broadband, I'll go through this a little bit quickly. Obviously, as Ed mentioned, the Internet of Things is a term like Kleenex or tissue. It's become synonymous with lots of different things, some of which have the original meaning, some of which do not. Let's say the connected world. And that's how Axiros addresses things as a software company. I'm not here to address it from that perspective, but as an industry, we are surrounded by, managed by, create revenue from connected devices. USP is a technology that's designed to harness the capability of a standard for that application. In the plural, for many different applications in our business. One of which is one that is kind of fun because I think Clark is probably here this year, but from CableLabs itself, Clark mentioned in 2014 a great quote that I came across when I was looking into preparation for this talk. And it is, Clark said that CableLabs believes the cable industry can leverage deployed equipment, services, and infrastructure, and that's true. We have a lot of that, to establish a strong foothold in the Internet of Things. Now, given the pace of technology, I thought that was particularly interesting from 2014, because look at here we are now, and even among the panelists, we've discussed the humorous, sometimes scary things that can become connected in a home, accidentally or on purpose, and there are a lot of things that need to be addressed. Managing them from an MSO perspective, not only for provisioning and control, but for security, for enabling services. So I thought this was particularly prescient, and give some credit where credit is due. Back in 2014, which is an age ago in the cable industry, I thought that was pretty prescient. So the Internet of Things as a living and breathing segment, if we were to call that connected devices, has a huge impact on us in the cable industry. And as we can see from these statistics, there are about $450 billion being spent in the American economy by our industry. And as I mentioned, an economist by training, I can tell you that number can range from half of that to 5 times that amount, depending on what you consider. We have some associations that do very good research. When you look at the impact of jobs, and you look at the impact of technology and how it transfers through this industry into the economy in general, not only in the US, but globally, it's as important as the space industry was in the 1960s. In current dollars, you might say that it's 3 times more valuable, which is incredible. So when we're taking a look at the difference in speeds that were required by infrastructure in our industry between 2007, which is when the iPhone came out. It sounds kind of not like a long time ago, but in the internet age, it's ages and eons ago. And to 2018, where we're looking at 2 gigabits per second, gigabytes, I should say. And so in 2016, the investment was about $0.7 billion just in IoT-related technologies. So if we use the phrase connected devices and IoT technologies, 2020 it's 1.3 trillion. That is an incredible difference. And that's what we're addressing here on this panel today. How do you harness it? What does it mean? What technologies are used to do so? So let's jump right into it. We have some connected homes. We have lots of devices that are being managed. We have different technologies that are being used to manage them. USP is one that I think has a great deal of utility. As a software company, we don't pick favorites. It's available. It has some interesting aspects for operators, manufacturers. It has the capability of allowing manufacturers and operators together to not only manage device but enable services. And that's one of the exciting things about this standard in a world where human nature sometimes dictates it's important to follow rules, and yet you want to foster innovation. The great technologies are those that are invisible. USP does a lot of utilitarian things, allowing us to manage securely connected devices to different management purposes, whether it's provisioning and operations or revenue enablement. And so that's one of the things that we'll focus on here. So the IoT is important to cable operators, and as was foretold, I think, intelligently in 2014, the cable industry is uniquely suited to take advantage of it. So I'll briefly introduce the, forgive me for talking fast, I want to make sure we stay on time, but the challenges I think many of us are familiar with here in this room, and they are the operational costs of new technology can be quite high. It used to be that the new line extender or amplifier cost was twice as much as the 400 megahertz device node or a line extender. Now, cost of implementing new technology is measured not only in the cost of the technology, but in the revenue lost. And with so many services being tied to connected devices in the customer premise, both things need to be considered. So it can't be disruptive, as much as that's a fun term in the software industry. When we're talking about implementing services or devices that enable services, new technology adoption needs to be done in a coherent way. We also have to deal with legacy technology. You don't have the choice of just replacing all the old stuff with new stuff that's better. That's not part of the equation in our industry. So USP enables a way to take technology currently used, both in the software side and in the CPE embedded devices, the clients and technology embedded in currently deployed CPE more particularly, and enables you to go ahead and extend that to a new technology like USP. And I'll explain a little bit about that. Did you have a question back here? No? All right. And support and maintenance. When we're talking about the cost of new technology, a standard, however great, needs to be one that can be supported into the future. So it needs to have legs. There needs to be risk that it will not fail, because everybody can create the next great app. But if you're creating a standard that's going to be used by an industry, as we mentioned earlier, that has had a jump to $0.7 trillion just within the span of the age of a phone in your pocket, that is a huge consideration that must be taken. So USP enables a whole home business approach to managing devices while taking care of the operational considerations that must be considered. And the operators and the security, the operators who need to be mindful of the security aspects, and we're going to have a little bit of discussion on that a little later, are no less important than what are the other revenue attributes that can be obtained by a technology. So USP fills a lot of check boxes. So let's get right into it. The evolution that has led us to TR-369 began back in the early 2000s with TR-69. Here's a little evolutionary table that describes the evolution of the standard itself. I'll just go through it for a bit of context. It was in 2002, 2004, where the technical report from Broadband Forum, then with a different name, I think it was a DSL forum, which is why it is in some ways kind of tidewaters that people still perceive as being different industry specific, but broadband has made all of that distinction really disappear. That the TR Technical Report 069 was established for managing devices. And it was a protocol that was established to allow remote management of devices in a customer premise. TR 181 is a data model, a device data model that is part of the TR 69 standard. When a lot of connected devices and a lot more connected devices became available for consumers and for operators to have as part of their business model, or nuisances that were purchased at Best Buy and stuck into your router, the data model in TR-181 became even more important, not only to TR-69, but now to TR-369. Why? Because in 2010, the data model evolved with TR-181, and it continues to evolve. In September, we already had some changes to the Device 2 data model, which is now Device 2.13, that enabled more IoT devices to be managed under that data model. So the TR-181 data model still remains part of TR-369, and it still remains part of TR-69. So the change in that device data model is applicable not only to TR-369 or USP, but also to TR-69. And that's an important consideration when we talk about the cost of adopting new technology. It's like getting great new tires on a car that's still fast, but it's not quite as shiny as it used to be. Well, if you just need good tires and the engine's still fine, you've reduced some of your technology debt. So this is the evolution in a graphic. I won't spend a lot of time here. It does what I just did in 3 minutes. But as you can see, the timeline indicates that the progression of this technology isn't accidental, unplanned, or without consideration for those things that we talked about earlier. It's in place. It's in over 1 trillion devices now, the TR-69 stack. TR-181 data model continues to evolve, and USP is now here. So what is USP? This is TR-69 and how it uses an ACS or a controller to communicate with a common protocol to a device inside of a customer premise. The evolution is necessary for those things that we just talked about. The scale is bigger, there are more numerous connected devices, and more importantly, MSOs and any broadband carrier needs to be able to manage devices in the home, but also those things that are connected to it. And that's become a big concern. So the attributes of TR-369 or USP that we were talking about earlier are flexibility, security, and scalability. We'll have some questions during question and answer period, I hope, that will come up that will shed some light on some of these things. But one of the interesting aspects of USP is that a multi-point to multi-point system. So whereas you might have a monolithic do-everything controller using fairly rich messages to query and receive responses back, whether it's for data collection or whether it is for delivering instructions, now you have endpoint to endpoint, meaning that you can have not only more numerous combination of ways to manage and provide service through a device, but you have ways that can segment responsibilities. And that gets into how you might manage risk and security considerations. The security we'll speak about, and standardization is clearly important. So, am I over?
Good.
All right. Well, I'll take you through a couple more points, and then I'd like to yield the floor. So the TR-369, the multi-point to multi-point, is important for this reason, and I'll show you the data model. So when we talk about the flexibility, we're really talking about the way that the technology can be used both on the controller side and on the embedded side. So in this picture, you can see the data model, and you can see that there's a difference between the message and the records. And that's important to separate the transport from the data. So with multiple capabilities for using different security levels for transport, you can also manage by accessing the data model directly just those things that you need to control, which eliminates a lot of unnecessary weight in a message. So in a MSO application, there are multiple uses for this technology. They can be everything from managing, things like Wi-Fi, where you have a need for ongoing persistent connections that are focused specifically on certain parts of the data model and not sending lots of messages, how are you, I'm doing fine, and looking for conflicts. This is a good description of the architecture. I'll just wrap it up here. So in TR-369, you have the ability to create endpoints on both sides, on the control and on the embedded side, and that's very important because a service element is comprised of instantiated data model, which takes the data model in 181 and focuses on just those operations that you want to manage. And that's a very important part of USP. So whether it is for any part of the data model that is in 181, you can create two different endpoints. Those endpoints can be controller to device. They can have controller to mobile applications in the cloud, and a multiple of opportunities exist for management. So I think with that, I don't want to take up more time than was allocated. I'd be happy to address any questions during that part of the session.
All right.
Thank you.
Great. Thank you, Michael. Let's see. How do I? Here we go. All right, so next up, we've got Brian Scriber, who is a distinguished technologist at CableLabs and the Vice President of Security Technology, where he focuses on security strategy and implementation. Brian's extensive experience in software security and cryptographic governance, and has led key security and privacy initiatives at companies across technology, financial, and healthcare sectors. From 2015 to 2019, Brian was the chair of the Security Working Group at the Open Connectivity Foundation, which is the topic that he'll be talking and sharing some details about the security and privacy aspects that that foundation is working on. So.
Yeah, first security rule is put a railing on. It's the edge of that.
Let's see.
All right. So I'm going to do an abbreviated conversation on, let's see if we can get that to start though. Hang on. Try that one, this one, that one.
No, it's giving us something up there.
Maybe just advances like that.
I don't know. Sure.
Oh, there's got something. Oh.
There we go.
Yeah.
What is that?
Thanks, Ed. I think it's,
I think you're good. You good?
we'll see.
Try that.
All right. We'll do it this way. There, it'll be good enough. Great. So, $5, right? What can you buy for $5? Magazine. In Denver, you can get 2 of these. In New York City, you can get 1. Some snacks, and you can get 1 minute on a pedicab in New York City. 1 minute. But the reason that we're up here and talking about security is I actually just checked. It used to be a 200 megabit per second botnet that you could get for an hour for $5. But now you can get a 300 megabit per second botnet. I saw some that were 350, 400 claims, but I didn't see a lot of cred associated with that. But this is all dark web searches, pretty easy to find. To be able to go and say, yeah, I want to take out my fellow gamer, and while we're competing, I'd like his traffic to be crap. So as network operators, that's a big deal for us, right? And the promise of IoT ties into this a bit. And I'm going to move super fast on some of this stuff because we do only have 15 minutes. But the goal here has always been, hey, let's make life better. Let's make life easier, right? We're going to get these devices because now I can see who's at my door, right? I can connect my medical devices. I have security and confidence in the communication that's happening between those devices, and I know that they stay in their lane on my network. But we know that they don't. So What do we do as operators? From CableLabs' perspective, we have been engaged in trying to push these 8 initiatives. So the first and most important of all of these things, because devices lie, is we push for device identity. So devices have to have an immutable, attestable, unique identifier once they're onboarded on the network. Now, we can talk about privacy and kind of the other balance of this and say, hey, maybe when it's not onboarded onto the network, we don't have to have that unique identifier that allows some tracking. But once that device comes into the network and we're trying to find it, if you're an anti-abuse team member and you're trying to track down a device, the newest botnets look for that type of activity on the network and change the identity of the device on you. So what we need is to make sure, nope, you're on my network, you're glued to this identity. You don't get to be anybody else, and nobody else gets to claim to be you. So we've pushed really hard on that front, and that enables the other 7 here. So with OCF, which is the Open Connectivity Foundation, and before, I'm not even going to let you look at that slide yet, because you'll pay attention to the slide instead of me. And the background on Open Connectivity Foundation, I've talked to this group in the past on this before, but it's born out of the Open Interconnect Consortium, which was a Intel Samsung-led initiative to try to, hey, let's define an interoperability standard that we can have that has security as a foundation for the communication protocol. And there was also the All-Seen Alliance, All-Seen and All-Join, which was the Microsoft Qualcomm-led initiative to say, hey, let's all get together and build an interoperability standard where security is part of the protocol. And they decided to go, different directions with this. CableLabs got involved. We were actually part of both of these and helped to kind of get the 2 of them and UP&P like, hey, everybody, let's get together and let's play as a single team and let's send a signal to the market that it's not 200 manufacturers and 200 manufacturers. But let's do this and say, look, we've got over 450 IoT manufacturers saying, yes, this is the direction. This is the North Star. This is the island that we're sailing towards. And it is an interoperability standard that has security as a core part of that protocol. So that is kind of the promise of the Open Connectivity Foundation, and we've been working on this for several years, and we've actually got to a point now where, hey, the spec, you're always going to be updating and hitting security and improving things, but the spec's at a really good spot. It's kind of, when you think about Sisyphus and the boulder, right? Sisyphus got to the top of the hill here, and it's at a good spot. There's always, more you can do, but really we're at a spot where it's like, all right, now industry, let's see some adoption. Let's bring this thing in. And then when that happens as a cable operator, right, what are you going to see and do with this on your network? What happens when a device comes into the network? And OCF and the Wi-Fi Alliance, the onboarding mechanisms, the idea here with the Wi-Fi Alliance's device provisioning protocol, also known as Easy Connect, trying to make that sync up and be really clean and a handoff from the Wi-Fi Alliance to OCF so that we can bring these devices in. They can talk to each other. You've got Cisco in here. You've got Intel, Microsoft, Qualcomm. You've got all these major players where you have LG and Samsung in the same room talking about how they want their devices to interoperate and communicate. I mean, it's a cool conversation to have because you've got this kind of co-opetition, which is a fun not word to say. And when these devices come into the network, how do you get that security that we're talking about, right? So the initial discovery, ownership transfer, provisioning, this happens through an onboarding tool. So when the device gets plugged in. You have a tool which is either through your hub, through your television. If it's a set-top box-based hub, you're going to look at the TV and say, oh, okay, hey, a new device just came on board. Do you want to bring in this new light bulb or this new washing machine? Yes, I do. I want to bring that in, and it goes through a very seamless handoff. Certificate-based exchange to be able to identify the device, make sure, yep, this is what it claims to be, and we've got that identity that we associate, and we bring it into the OCF security domain. Inside the device, how am I doing on time? Inside the device, there's a state machine where the hard reset, the device, when it comes from the manufacturer, transitions to this ready for ownership transfer. So that's the, hey, I'm ready to bring this device into my network and own it. There's a provisioning that happens. And especially if you've got some of this with like the device provisioning protocol with the Wi-Fi Alliance and Easy Connect, a lot of this happens under the covers. So the user experience, it's really a transparent security. And the fact that we're using certificates, the fact that we're doing all of this in the background and only telling the user if there's an error, and allows them to be able to say, yes, that is the device I want. They do have to authenticate and say, I really want this on my network, because otherwise you could bring a device to your friend's network and bring it on and have malicious entry into the network. But we want to keep it as simple as possible during this provisioning. After provisioning, it moves into that confusingly named RF NOP, so ready for normal operation, and that's where the device spends most of its time. It hangs out in normal operation after it's been brought into the network from provisioning and into the OCF security realm through that final provisioning. There's some resets that can happen and some changes to the device, hard resets and soft resets, but for the most part, this is the kind of the main transition. So when we talk about access control, there are a lot of different ways to attack this problem, and the OCF uses both RBOC and SBOC. The role-based access control, where we're saying, hey, this is a device that is it's a sensor, and you're going to associate sensor. It shouldn't be, unlocking your front door. So if you've got a bunch of sensors, group them as sensors. You have a bunch of light bulbs. Hey, these things are light bulbs. But you may have some security devices that you may want to give special provisioning to, so you can associate ACLs on the specific device, or you can group things together and manage them. But it's really, without going through how ACLs work, it's ACL based, and it checks during the onboarding. There's a credential management service which provisions new credentials on the device during the onboarding, and there's also the access management service which does the access control to find out, hey, for some reason you bought a smart toaster and you connected it to your network. Should that smart toaster be able to connect to your front door lock and unlock it, right? Probably not, right? There's probably not a good use case for that. And so you would want to make sure that your access control didn't allow something like that. The kind of quick overview on all this, for OCF, all communications are signed and encrypted, so we don't have concerns about tampering, replay, or eavesdropping. The unicast messages are encrypted with and secured using DTLS or TLS, depending on what capabilities that device may have. Multicast messages are broadcast. So with OCF, if you're doing some discovery and saying, hey, is anybody out there? That is an open message. But as soon as you want to access a resource on a device, that resource access must be an authenticated connection. So it has to be secured, and it's subject to the ACLs. So you can't ever view or change resources that are protected on devices unless that device said, hey, I want to make this particular resource a read-only, public, let anybody come and look at it. So you can kind of force the issue if you had something where well, let me back up for a second. Most of what I'm talking about, particularly for this audience, is smart home. So I should have done this at the beginning. IoT, really big, means a lot of things. I think Michael did a great job explaining that. Talking about smart home and IoT here and how we use it. There are some interesting industrial, commercial, enterprise applications where you may have some things like in a shopping center, a standee that wants to be discovered and you want to make some resources public. But for the most part, you want to control access to all the resources inside the smart home. I think we've kind of covered that slide. An interesting thing that has happened is of late, the CTA has pulled together a group of all of the IoT standards bodies to talk about what's happening in IoT, and they are starting to classify your networks as strategic assets. And that can be a dangerous place to be when the federal government or any government, they're here to help. Right? But when that happens, it complicates things usually, it can be dramatically. And why is the government engaged in the IoT discussion? Kaizen, which is a management philosophy, drives to this ask why 5 times, right? Why are legislators looking at IoT? Well, the network's getting attacked. Okay, why is that happening? These things are easy, they're cheap. And we keep driving all the way down. And the real issue here is there's an economic, almost disincentive for a manufacturer to want to build security into a device, certainly to update the security of that device. So every update after they sell the device hits their bottom line. And the idea of, hey, let network operators manage the problem that we create on the network, that's not our problem, is an unfair business practice, and it's one that as network operators we have to push back on and say, no, that's not okay, right? It's your device, you're selling it, it's your job to make sure that that is a securable device and that you actually have secured it. So what we're trying to do is make that very clear here and say, no, we've built out a solution. How do you fix the IoT problem? You do it not by creating a big spec and saying, here it is, everybody, here's the standard, we're all going to use it, and there's a whole bunch of other standards out there. You do need to specify what you're doing, but you also build out alongside it a reference implementation, and with the Open Connectivity Foundation, the reference implementation is a Linux Foundation project called IoTivity. So if you're going to contribute to the spec, you're also going to contribute working code that must pass tests inside IoTivity to make sure that this is available. That way, a small business, an entrepreneurial company where the CFO is asking the CTO, how much does security cost us? The CTO can say, you know what? I got the whole stack. I got it for free. I got 90% of what we're doing. I'm just writing the application layer on top of it for our device. It would cost us more to take security out than it would to add security. So we're not going to go and require somebody hire a crypto expert or a network security expert. The Open Connectivity Foundation's had all of them gathered, and for 4 or 5 years now, driving to this specification and this implementation. So from that perspective, oh, there it is. Back to that promise of IoT, right? Can we deliver this? Can we get this into the hands of manufacturers and entrepreneurial companies that are coming up with these new IoT devices? This is obviously a future path. We have to deal with the devices that are out there now, but in the future, can we get to a spot where as a cable network, we say, nope, you've got to meet this bar. You must be this tall to ride this ride. And if you don't have security in your devices, you're not coming on this network, or you're not going to have the same level inside this network as other devices that do have that security. So with that, I'll yield the floor. Thanks.
All right. Thank you, Ryan. All right, let's see if I can get the next slideshow up and running. Yeah, we're good. Okay, so next up we've got, last but not least, we've got Ryan Cunningham from Comcast. Ryan's a hardware design engineer in the Comcast Product and Technology Organization, where he focuses on the overall architecture of IEEE 802.15.4, which I'm sure he's going to educate everybody what that means. So products related to that and systems associated with IoT, including Zigbee, BLE, Thread, Wi-Fi, LTE, and LoRa. So with that, I'll welcome Ryan.
Okay, want to click start here and then. Yep. Cool. There we go. All right. Hello, everyone. I'm Ryan, and today I'm going to be discussing the performance benefits of consolidating IoT traffic into the gateway. So the smart home continues to explode. More and more devices continue to add wireless connectivity, from light bulbs to fridges to microwaves, and each of these devices all have different forms, fits, and functions, and require different protocols to be able to develop them to have the performance that they're required to operate the way that they need to. And what this results in is that the end user is, by getting all these devices, creating an ecosystem that has multiple protocols. And from a service provider perspective, it's imperative from a user experience perspective to have these protocols able to coexist with each other, and taking those types of considerations in mind when you are developing your products. Excuse me. Now, for example, a low-powered battery-operated device is going to have different requirements than a high-throughput device. And for instance, Bluetooth would be more optimal for something like that, as opposed to Wi-Fi for a streaming device. And it's, I'm sorry.
Was it not advanced?
Not, sorry. Yeah. Oh, sorry. So moving on. So what I'm going to be covering today is I'm going to be focusing on 4 specific IoT protocols, which would be Wi-Fi, BLE, Zigbee, and Thread. And the reason I'm going to be focusing on these is because most of them are co-located in the same band, and as a result, it's extremely difficult for them to coexist. So now Wi-Fi, as I'm sure most people in the room are familiar with Wi-Fi, is ideal for high throughput applications and operates in both 2.4 and 5 gigahertz band. Now, depending on the quality of the link between the devices that are connected to the gateway will dictate whether or not it's able to be connected on 2.4 or 5 gigahertz, et cetera. In the ideal scenario, because of the larger amount of space in the band, it would be preferable to have the Wi-Fi devices connected to 5 gigahertz. Now, you can't always count on that, and as a result, sometimes you are forced to have devices connect on the 2.4 band. And that has significant challenges in terms of coexistence capabilities with other protocols such as Thread, BLE, and Zigbee. So now 802.15.4 is the MAC and the PHY layer of these Zigbee and Thread protocol. Now this is intended to be a low power and low cost implementation that is typically used for battery operated sensors, and such as a door window sensor, a motion sensor, etc. Now The key metrics, performance metrics for these type of devices is that you need to make sure that as you're having an event, so for instance, a door window sensor, let's say, when that action occurs, the latency associated with how long it takes for that action to be reported back to the user would be the first key metric. And the second would be, as I said, most of these devices are battery operated, so how often the frequency that the battery needs to be replaced for these devices. So now, keeping that in mind, a lot of these devices, to be able to accommodate that, particularly for the battery operated aspect of this, they are sleepy end devices, which means that they're in a sleep state where they're not having the receiver on, and essentially, based on whatever the operation or the purpose of the sensor is, they would wake up and then be able to report that information back to the end user. So the challenges associated with that from a coexistence perspective is that you are not necessarily easily able to change channels and have the frequency agility that you do in other protocols, because by changing a channel and a device does not have the receiver on, might not actually be able to determine that it has switched channels, and what that will result in is that a notification would be attempted to be sent on what the device perceives as the current operating channel, and would end up having to rejoin the network, and then it would be a very bad user experience for the end user, as the time associated with that would be large. And then there's also battery implications that would be involved with that, having to retry, retransmit, sending that packet over multiple times, and that would be the other metric that would be affected by that, which is not good. So what typically ends up happening is, for these networks, during commissioning, a channel is established that is perceived to have the lowest noise, and it ends up operating on that for the majority of the life of the device, unless for some reason it is manually changed by there's perceived issues, or battery life is not where it needs to be. Now, BLE covers a very similar use case in terms of the devices that it is covering. It's also going to be catered towards low power sensors, typically battery operated, but the way that it tackles coexistence is a little bit different than 802.15.4. So rather than taking the approach of typically staying on one channel, the idea is that it hops around the frequency spectrum, and the idea being that if it doesn't get it through on the first try, that the packet and the message will eventually be received by changing channels frequently and over time, and the hope that you wouldn't have to focus on having a perfect link at the moment that you're transmitting. Now, the way to be able to start mitigating and understanding how you can coexist in a gateway is understanding how these devices are coexisting on a physical layer. So what that means is, how are these devices able to communicate concurrently? Can they? Are they able to? And under what conditions can they? So an example would be, if you're having your Wi-Fi network on channel 1 and you're having your Zigbee network or Thread network on the upper end of the spectrum on channel 24, 25, which would be about 2475 megahertz, and the center frequency of Wi-Fi being 2412, you have about 50 megahertz of spacing between those channels. But there's still going to be, when Wi-Fi is transmitting, especially in a device where you have the radios next to each other, while Wi-Fi is transmitting, the energy detected at the receiver of those other devices is not necessarily going to be at the thermal noise floor. So that means understanding where your devices are placed relative to the gateway will dictate whether or not a device could be able to actually demodulate a packet from a Zigbee device while Wi-Fi is transmitting, et cetera. So understanding that is the first key to being able to determine how well you'll be able to coexist, and where you need to set up your networks for these different types of IoT devices so that they can effectively coexist together. Now, the easiest way to be able to understand that is by taking a look at what the signal to interferer ratio is. So depending on what the device of interest is or what you are attempting to evaluate the ability to coexist, you would take, say, a Zigbee network on the operating channel that you're currently evaluating, and then you would choose or be evaluating, let's say, the impact of your BLE network in the same box. You would take the center frequency of the signal of interest and the bandwidth that signal is occupying, and then you would estimate what the power spectral density is of the interferer over that bandwidth. And the goal would be trying to understand, do you have sufficient enough SNR while that device is operating based on what the side lobes and the roll-off is of the signal that's interfering. So for the assumptions, like you'd be assuming in most cases that you ideally would not be having a co-located channel. That makes it a little bit more easier to understand and to get a pretty good idea as to how well these devices will coexist. So with the assumption that you're typically having these devices either adjacent channel, meaning that you're not co-located in the main lobe of the interferer, but you're next to it or have a decent amount of space, it would be understanding what the energy of that spectral roll-off is at the device of interest. Now, by understanding all of those aspects as to basically what devices can communicate concurrently, what can I have my Zigbee door window sensor communicating at the same time that I'm streaming Netflix and not have significant performance impact. Then you can start taking a look at network management techniques. So which devices can physically operate concurrently, and there's, based on the protocols for Zigbee and Bluetooth, there's timing constraints that you could, so for example, BLE has connection intervals. So understanding that I have mandatory packets I'm going to be expecting at a specific interval, or by using machine learning or other things to understand when a user might typically be doing certain actions, you're able to schedule that. Now, one of the large challenges with the scheduling is that predominantly a lot of IoT devices have stochastic behavior, meaning that you don't necessarily know when the events that you care about are going to happen. So it's going to be difficult for you to predict when you would expect someone to necessarily be walking through a room or opening one of your doors, triggering one of your sensors. So although the scheduling can help for the probably bulk of the events that are used just to provide status updates for these devices, they don't necessarily alleviate the issue of being able to ensure that the actual message that the user is caring about, the event, is going to necessarily have enough time to be able to address that. Now, OFDMA is, with 802.11ax, helps with this a lot. You're able to basically allocate specific resource units and schedule them over time and frequency. So basically you can take a look at if you have an 802.11ax system implemented with an IoT system in a gateway, you would be able to say which of my Wi-Fi clients that would be not able to concurrently communicate while I am having my Zigbee devices communicate, and you would be able to dynamically schedule those RUs so that you would be able to ensure that for the bulk of your traffic is able to communicate without interfering with the other devices. So another key aspect and one of the benefits that you have by consolidating your IoT traffic into a gateway is optimizing channel selection. So similar, going back to the physical layer coexistence, by understanding how far away the devices, the channels are spectrally from each other, you can make a more intelligent decision as to what the requirements would be for these devices to be able to communicate concurrently. So for instance, if you're not expecting to have a lot of traffic on your Wi-Fi network, you may be able to have it closer spectrally to your IoT devices, because from a time and probability perspective, you may not be as concerned that you will not be able to get your packets through and have the critical information that the end user needs to be able to, have a good user experience and get everything reported to them in the way that it needs to be. And then another opportunity, and this is typically depending on what type of devices you would have connected to your gateway, would be prioritization. So for instance, if you're having just a light bulb or non-critical devices connected to your gateway, that's not necessarily as important as if you, say, had security devices connected to your gateway. So the way that you would select your channels or do your scheduling most likely would be impacted by which devices are the most critical for your system. So is it more important for you to be able to ensure that you are able to stream Netflix in 4K over a certain period of time? Or you may have a specific requirement with regards to security that you need to make sure that you are able to get a notification that your door was opened at night while you're sleeping. So depending on your use cases, you can take the flexibility to be able to allocate where your networks need to be and how they need to be set up so that you can coexist more easily. Now, another, which I think is probably one of the more important or the largely more valuable aspects of coexistence, is the ability to be able to spatially map where your devices are and really get a good idea as to what your ecosystem actually is. So when you're having your devices connected to your gateway, typically, or even if you had an individual subsystem of multiple devices, and you would be able to know based on RSSI and basic link information how far away your devices are from your gateway. But it would be more of it's a static distance of X, and you could extrapolate that based on what you would anticipate a typical path loss to be from walls or et cetera, from a typical home. What you don't know is the relative distance of those individual devices to other devices. And so you could be understanding how well you're coexisting from just the gateway itself, but you also need to be cognizant of how well you're coexisting to the client that is connected to the gateway and the spacing between that client to the door window. And that comes into account when you're going through scheduling, channel selection, and understanding basically where everything is in your house, which you're able to do by having all these radios consolidated into the gateway, because you can basically, using various techniques. So for instance, Bluetooth now has, it was either 5.1 or 5.2, they added localization where you're able to basically estimate what the angle of arrival is, and meaning what is the angle that signal came in. You can basically create a map as to where everything is. So to conclude, if you consolidating all these radios into a gateway gives you the opportunity to really create more of a map of your ecosystem in your home. And it gives you more tools and knobs that you can turn to allow these devices to be able to coexist more effectively, because by understanding in a central point where things are, and you also are given the ability to control them more easily. So with that, I think.
Great.
Yep.
Thank you, Ryan.
Thank you.
All right, so now we enter our interactive portion of the conversation. So at this time, I've got some questions, but also would love to hear from people in the room. If you have any questions, just step right on up to the blank microphone area. I've got a microphone here. If someone wants to run it down.
Approach.
Start My voice is loud enough. I don't need a microphone. I just want to ask you with the, I'm sorry, with the evidence of 6 gigahertz being deployed, do you think that that's going to help in coexistence in the future for homes and systems?
Oh yeah, I mean, ideally, you would figure that you would,
You just want to put it up there.
Excuse
in the
me.
center.
ideally, you would want to have as much separation spectrally from all the other devices that you're trying to coexist. The majority of the issues or the techniques that were discussed with regards to coexistence was primarily because those devices were located in band, and it's extremely more difficult to be able to coexist in band just based on the amount of energy that you would see with things that close in proximity to each other. So yeah, having more space spectrally would definitely increase the ability to coexist.
Thank you.
Yep.
Great. Any other questions?
Yeah, I hate microphones.
Oh.
Stand up. Hey, Ryan, you talked about safety in the 2.4 gig space. So my name is Mark Barnett. I'm from Tempo Communications. We are seeing more and more of the 2.4 gigahertz space is just absolutely saturated, congested, interference, things like that. You talked about the Zigbee systems because they sleep. They're really not very good at channel changing. What are you seeing in the industry as the 2.4, especially in the MDUs and even in residential, as the 2.4 becomes more and more congested? Are the Zigbee security systems primarily, are they able to communicate? How are they managing that congestion?
So a lot of it comes back to, there's kind of two schools of thought, in my opinion, as to how you tackle having a low power design and optimizing for battery life, which is obviously very important to be preventing having to send someone out to replace a battery for a security system. So one approach is that you have either extremely low power transmissions so that you can just basically retransmit for a very, very long amount of times, just assume that eventually it'll get through. And that has kind of, in my opinion, a little bit more of a poor experience, it's depending. So I think that part of what is going to be able to help with that is having higher power sensors that are able to coexist better at farther ranges, where you aren't as concerned about having to have sensors down in like the minus 90s or sensors that are very, very far away. By having that additional power, you have more margin on signal to interferer ratio, and it provides an easier platform for them to be able to coexist. I think that that's what makes it the easiest to be able to alleviate that type of concern with all the congestion. And especially since these devices are typically, they're not streaming devices. It's usually a kind of a one and done where you just want to get that notification through, right? So it's because of the sporadic and the stochasticity of that, I think that that's the best way to handle that.
Hi, I'm Clark Stevens from 2014.
Well done, sir.
I have a question for Michael. So the USP stuff, is that designed like the other TR stuff where it's primarily meant to do management stuff, or is it meant to do sort of operational communications as well?
No, good question. So the answer is both. The technical reports are what one might call a standard, right, for a protocol or that mode of operation. What's happened with USP, particularly TR369, is that it's utilizing the 181 data model, which has a lot of operational access to the functionality of the device itself. And what it's doing is it's creating an endpoint-to-endpoint structure so that that standard can be applied by operators during implementation, manufacturers by design by their implementation, and it creates a standard way to do all of the different things possible using that data model, that device data model, while at the same time enabling several different transport security layers and mechanisms so that you can use, we heard TLS and DTLS, you can use a lot of the same type of language development environment and systems that are currently in place to use an IoT application. So, Ryan had some very good points about consolidating an IoT environment around a gateway. One of the ways that USP can be used to do that is by managing different protocols, Zigbee, Z-Wave, Thread, that might be present, already available in devices in a home or in an industrial setting, and creating a structure not only to provision the device, using that part of the data model 181 in USP or TR369 that enables provisioning, but also to make smaller the messages and the data for very specific operations, even for different modes of operation for that device. For instance, a gateway to an IoT sensor that might use Zigbee or Z-Wave or LoRa, and also managing the Wi-Fi environment. And as Ryan did a good job of mentioning, and Brian talked about security, all of that becomes important, particularly when you do consolidate operations around a gateway, whether it's in a residential setting or an industrial setting. So that's what the TRs are now kind of doing. They've evolved into focusing on what is a practical real-world application that's likely, and then making it available to operators and manufacturers. And so for software companies, then, they're free, whether those are in-house or outside, to implement them in any way that makes sense. Good question. And well done in 2014.
Question. Brian, you mentioned immutable identity of devices.
Yep.
So how do you see, like to Brian's point about these Zigbee devices needing security, how do you see the requirement to have this immutable identity filtering all the way down into end devices? Are you looking at that?
So, one thing that there ends up being a number of things that in 15 minutes you've got to leave out, right? The idea of OCF is that it's transport agnostic. So, to the points Ryan was making, hey, you're using 802.11, you're using BLE, you're using Zigbee's transport layer, right? There are some different tiers to Zigbee. From that perspective, we don't, in the OCF world, we don't care how the transport works. We are basically network to session layer integration and building that out. So when the device comes on, it's gonna, you're provisioning it into the network, you're telling it, where to talk, who's in charge, you're gonna do a credential exchange. When you do that credential exchange, yes, you have to bring that immutable identity, unique, immutable, and attestable. So that's kind of the other part, right? If you can say, you have to also show me you have proof of possession of your private key for me to trust that this is really you. And don't give that to anybody else, right? Never share it, and then you have, nobody can spoof you, and you can't pretend to be somebody else. And that's the kind of thing that inside the network, when you're, as I was mentioning, in the anti-abuse business, and you're trying to track down a malicious device, when those devices are watching for your scan traffic and saying, oh, things are getting dangerous, I'm gonna quick become something else. And there's code out there with some of these botnets with Mirai variant, Demon Bot, like some of those have some code in them to say, if you're seeing network traffic that looks like this, begin the switch protocol to pretend to be some other device. And they're common devices. So, you're looking at your network, you're like, yeah, those are all good devices. Where'd that bad thing go? So that's the thing that we're really pushing for with the identity.
Yeah, and you said keeping devices off of MSO's networks if they don't meet that.
Well, I think, so this is where, there's a difference between a managed home and, consumer devices. And inside a managed environment, you have some flexibility if you're an MSO to be able to say, inside this space, you have to meet these requirements. If your device does, it gets, preferential treatment kind of thing. If you've got a malicious device and it starts becoming part of a botnet, right? You've got to be able to defend your network, and you have to be able to say that is not appropriate, and how do you effectively shunt that somewhere where it can't do damage, or at least like best case is that you narrow it down to the port that traffic's coming off of, and the rest of the device functions normally. But the worst case is what we have today, where it has to be a phone call to the house, and you're telling the subscriber something in there with a MAC address of A7, go find this thing, by the way, and it's behaving poorly and sending a lot of traffic. Until you can fix that, we have to shut you off. Well, 5 years ago, maybe 10 years ago, you could turn off somebody's internet because it was their web traffic and their email. And now it's their medical device is talking to their doctor, right? And so turning off somebody's internet because of an abuse situation is untenable. So you've got to have other tools available, and this is part of that path down to here, it's this device. And when it onboarded, it used this certificate, and you called it Living Room Light, right? Oh, I'm gonna go unscrew Living Room Light. Now can I get back on? Like, those are the things we want to enable.
So just a little follow-up question on that. So on the topic of security around the devices and what OCF is proposing, and then on the IoTivity side, right? So the fact that the contributions are made in open source, if you're going to participate in OCF, how do you keep that device security secure in an open source environment when there's always been in the past a security through obscurity kind of approach, when now it's out in the open?
And I love this question. So if anybody's ever using homegrown crypto, right? Like, oh, we made this ourselves. We got a guy. He's really smart, right? That's the scariest phrase ever, right? You want cryptography that has been vetted, tested, that people have been banging on for 20 years trying to figure out, hey, are there any flaws here? But the brand new, we got a guy, is a terrible model. Now, what we've done in OCF is say, hey, we are going to take these well-vetted cryptographic approaches, and we're going to use the asymmetric cryptography. And we're going to use libraries that are there, and because it's open source, hey, these are visible. You can go in and you can look at it. The argument of, hey, everybody's going to go and review it, that's going to be great, is not one that I think stands up, because there are very few security engineers in the world, and we don't have a lot of time to go look at everybody's open source. So it's not like it magically gets fixed because it's open source. But because we're using these public libraries, and because of the nature of asymmetric crypto, where I can have a conversation with somebody in the audience, and we could do it right now, where we do a public exchange, and we end up with, everybody's listening to everything that's said. We do an exchange, and we end up with a secret afterwards that nobody but the one person who's answering my queries is privy to. So it's that same kind of technique, Ed, that we're relying on the fact that it's public and that it's open source to drive some of that.
Unless I steal your device and read your private key.
Yeah, the storage of credentials is always one of those things that you can push and yell and scream, and if devices start to not do that, you're going to know that as an operator or as a consumer and say, we're not doing this anymore, right? And feedback like that with OCF, in order to stay credentialed, so if you're going to put the OCF logo on your device, which is a consumer-facing logo, if you're going to put that there, it means that device has gone to one of 7 approved global test labs that are literally around the globe, and they've looked at it, tested the device, and you don't have an open security issue like that. Like if you show up and we find out, OCF finds out, oh, you haven't protected your credentials, but you've signed this thing that says, oh, we protect the credentials, and the lab has said, yep, you protect it, and we find out you don't, then that credential gets pulled.
I had one question for Michael on OSP, or USP, sorry. So as a platform to manage devices around IoT, and there's always this discussion around explosion of IoT and how many devices are going to end up in the customer's home. It started out with a handful, now we're getting to 20, 30, 50 devices within a home, and continue to expand, and the number of devices is expanding. How does that platform, that technology, enable us to scale, the operator to scale, to manage those type of devices? Does it have the flexibility to get to large number of devices and a wide disparity of type of devices? And how does it help with that?
Yeah, good question. So there have been several good technical sessions here this year. One yesterday was focused on edge computing and the need for MSOs to distribute computing based on gaming and other high utilization uses. USP enables use not only in managing devices in the home, CPE, and that type of thing, but also Internet of Things devices, widely dispersed gateways that might be managing millions of sensors, for instance, by enabling small records that focus on only a very specific application. So it addresses it not in the messaging. It also addresses the scalability factor by enabling that same framework to be used for lots of different transport protocols. And that's particularly important with the Internet of Things and scaling, because as Ryan pointed out, there might be in a sensor very good application for a Zigbee or a Z-Wave or a Wi-Fi device. So in scaling, you need to not only consider the radio environment and the application, but also how you're going to manage the device, the data, use RSSI and maybe other technologies to look at neighboring radio signals to understand how that's going to perform, but also managing all of those devices in a uniform way. So the multi-point to multi-point framework of USP allows for a secured transport layer. It allows for small records, and it allows for 256-bit security. So end-to-end security, so even if it's persistent connectivity, the security aspect is addressed as well. So it's ideal, in fact, for scalable applications. In an MSO environment, it can be enabled first using an ACS and TR69 and 181, and as more controllers are developed to manage multi-point to multi-point applications, and the agent gets distributed out into the ecosystem, which can also be consumer devices, which is one of the cool things about USP, like TR69, the stack. Once it's out in the world and it points to a controller for a specific application or for many, it's manageable. And as Ryan mentioned, the management of a radio environment inside a consumer home is very important. You not only need to manage the devices that you've deployed, but devices that people connect to it. USP allows for having an agent in the consumer slipstream once it gets involved in manufacturing that MSOs could then utilize to manage as well.
Great.
Michael,
All right.
with that multicast secure messaging, it's got to be symmetric crypto then, right? So there's a shared secret?
It uses so it depends. So whether it's TLS or DTLS, usually it'll be session oriented, and once there's a MAC, once the message is authenticated, then that encryption will stay persistent. If that ever breaks, then it isn't allowed to communicate anymore. So in your scenario where you'd shut down a population of devices or MAC addresses, it's the connection. If it's once authenticated to be known, then it will remain persistent and open, and if it isn't, then it'll be shut down.
All right. With that, I think we're a little over time. Thank you to our presenters today, and thank you for coming.